Okay, so my job today is to teach you how to prove something, except in a special way. What did I say it was called? Proof by what? Induction. All right. So a proof by induction is different than just a proof, and it's got a specific three-step process. All right. Step one. Pay attention. I was okay with you talking before, but you need to stay with me now, or you'll get really lost. Step one. Write this down. Step one is you take whatever you're going to prove, and you prove it works for n equals 1. All right, so let's take something that we believe is true. Now this, do you remember those series where if I added 1 plus 2 plus 3 plus a whole bunch of things, I could just keep adding them up. You know, this is going up by 1 each time, right? So I could keep going in as far as I wanted. So I'm going to say until I hit n. N will be my last term, okay? And n helps me generate this list. Prove that that is really the same as taking n times n plus 1 all over 2. All right, so if we're going to prove this, first you have to understand it. If I put in like 5, and I think it means this, if n is 5, then do you get it's not 1 plus 2 plus 3 plus 5 makes 5 and 5 plus 1? Do you get that that's not what's happening? Okay, what is happening? Well, let's just keep the simplest case. If the simplest case is n is 1, let's try to understand what that means. If I put a 1 here, do you get it's not 1 plus 2 plus 3 plus 1? That whole left side is just 1. Okay? If I put in a 1, the whole side here is just 1 because there's only one term. What if I put in n is 2? What do you think that means about this side? It's not just a 2. It's 1 plus 2, which makes 3. If I put in n equals 3, are you catching on? If I put in n equals 3, then what would be on the left side? 1 plus 2 plus 3. If I put in n equals 4, I'm hoping you're catching on here because some people still get the confused look on their face. If I put in a 4, then that means all the ones in front of it and the 4. Okay, so 1 plus 2 plus 3 plus 4. All right, so let's do it for 4, just for the fun of it. Okay, so let's do 4, and let's stick in a 4 here and a 4 here, and let's see if this thing is actually true. 1 plus 2 plus 3 plus 4 should equal 4 times 4 plus 1 all over 2. Is it really true? Well, I'm not going to be proving that it will always work, but I can prove this formula works for 4 if this actually comes out right. Well, let's actually add them up. We can do that. You've been able to do that since like first grade. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. Did you get 10? Okay, and then on the other side, 4 times 4 plus 1 is 5. 4 times 5 divided by 2, 20 divided by 2, it's 10. Look at that. It worked. You know what I'm saying? All right, so I just wanted to show you one on the side that's if I put in 4. I'd have 4 terms on the left side. Okay, so that's a simple one, but let's talk about how we always start these proofs. We always start them by checking the simplest case, which is that n equals 1. So again, it's not 1 plus 2 plus 3 plus 1. If I put in n equals 1, I only have one term. So all of this is just 1 equals, and now I'm going to put in n equals 1 over here, and you should do this too. If you just watch me, you'll remember 10% of what I am telling you. Do this. This is a great example, and I've only got 3 examples. This is example number 1. I have stuck in 1, and lo and behold, it's 1 times 2 over 2, which is 2 over 2, which is 1. Yay, I proved it. Now, have I proved it for all times in all cases? No, but I proved it for the simplest case, which is if I stick in 1, it works. Okay, step 2. Step 2 is where you say, what if I want to generalize this? What if I want to let n be anything? What's another word for anything? Well, it's a variable. But I've already got a variable for n. I know this seems kind of pointless, but we need to set n equal to a variable. And the variable you always will choose when you go the IB route, HL, you're always going to use k for this. This type of proof, you always use k. There's no reason it has to be a k. They could use an m, but they just use k, so I want to get you used to it. Just kind of like in calculus, they always do substitutions with a u. Do you remember me saying let u equal blah, blah, blah? Anyway, u substitution is a thing that we'll get into more as the year progresses. All right, but you just always use u in that case. All right, back to, we just, on step 2, let n equal k. All right, it is as easy as you would think. You just stick a k in where there used to be an n. So I'm going to take this original statement here, and I'm going to rewrite it with a n instead of a k, or sorry, a k instead of an n. So I'm going to say 1 plus 2 plus 3 plus dot, 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 k is equal to k times k plus 1 all over 2. All right, so what we're trying to say is, okay, we tried it with a regular number. It worked. Now we're going to stick in a variable because we want n to be any random number that we pick. And if it works for that, and it also works for step 3, the next one after that, then you've proved it by induction. Okay, what's the next one after that? Well, instead of n being 1, we already proved that. N equals k. Well, since k and n are just a swap of each other, I'm not going to ask you to try to prove this statement because it's the original statement we had in the first place. But if we can now prove that it'll also work for the next number after that number, then it'll work for everything. Okay, so what is the next number after k? It's like k could have been 7, and then it would be 8. So how do I say that in terms of k? K plus 1. So your next step is to always say let n equal k plus 1. And that's saying, okay, we've picked k can be any random term, and now we're going to see if it works for the term right after the random term that we picked. All right, so now what do we do? This part blows a lot of people's minds, so stay with me. I'm going to take this side first. And now, considering we're going to k plus 1, we would have 1 plus 2 plus 3 plus dot, 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 plus k. I should have a little plus here, even though it's kind of redundant because there's pluses all over the place. Plus k. But then, don't replace the k with k plus 1. Would you agree there would be a k, and then after that, there would be a k plus 1 in the list? So all I really did was take this and throw in the next term, because k plus 1, I could throw it in parentheses here. K plus 1 is going to be the one after k. Could I also put a k plus 2 after that? Sure, but that would make it much more complicated. So we're just going to do one term more than any randomly chosen one. So we do the randomly chosen one, and then we do the one after that. Okay, so all we did was take this side and add in an extra k plus 1. All right, then it's equal to, didn't we just say right here that n was equal to k plus 1, sorry. Right here it said n equals k plus 1. And right up here we said n equals k. And therefore, you can put the k plus 1. Since k plus 1 is also equal to k, I'm going to put it right there and right there. I'm going to put the k plus 1 in for k, where that k used to be. Now I'm going to put in, there used to be a k plus 1, so I'm going to put, instead of k, k plus 1. And it's all over 2. This is one of the most confusing concepts that there is. And the happy news for you is that it's not going to be on your test because you already had your test. for my kids, for my students, I had already given this test, and this is going to be something that's given after the test as a separate little thing that's going to go in the grade book and not be worth a lot, okay? Because it's only one little part of a test. So I'll do something with this since we're done with the test already. Now, for those of you that have got a different teacher and you're about to be tested and it includes induction, well, and you have to be ready for this. So, all right. Now, I'm not even done yet. All I did was put a k plus 1 here, and a k plus 1 here, and a k plus 1 there. Really, it sounds kind of complicated, but I just stuck in a k plus 1 in 3 spots. Are you with me so far? Raise your hand if you were with me so far. Okay, good. Why didn't I put it where I had k? Because, remember, this is a list. And what's right in front of k? Yeah, or after, or whatever. Yeah, what's right before k plus 1 is k. And couldn't I, if I really wanted to, what's the one in front of that? Kind of weird, but k minus 1 would be in front of that. Okay. All right. So remember, that side's a list. That side's a list, which is different than the right side, which is more like a classic formula. All right. So now we're putting in a k plus 1. We've got that part done. Now, how do you prove this is really equal to this? Well, you could just manipulate, try to move things around, but the part that's really weird is this whole list thing. You know how this list thing is so weird compared to being a regular formula? I'd like to get it out of there. And that's what you need to do too, is get that list out of there. What can you substitute in for that list? I'd like you to look up here. Do you see something we could substitute in that's exactly equal to this, but is more of a formula? Yes? Yep. It's right here. Do you get it? Says equals that right there. That's the same exact thing. That's what I was looking for. That is that. Okay, so couldn't I replace all this with this? Yes, I can. And that's what I'm going to do. All right, so I'm going to replace all of this right here and put in that. And I'm going to have, clean this up a little bit. Get this out of the way. All right, so I'm now going to have k times k plus 1 all over 2 plus k plus 1 is equal to, and I'm just copying now, this is exactly the same, k plus 1, k plus 1 plus 1 all over 2. So this part that was the list needed to go so that I could have equations. Now, I replaced this with this, and I put it here. That's why I can do it, because they're exactly the same as each other. So it's a substitution. It's like taking out $1 and putting in 100 pennies. They're equal. Okay. So now, final answer, you have to manipulate this thing until it's exactly the same as that. All right, so what's the first step? Hint. Got to find a common... Oh, you have a question first. Wait a second. We need to find a common... What do you think? Denominator. Do you get that this has a denominator of 2, and this really needs to get added together so that it has a denominator of 2? And so your first step would be make this, put it over 1, because that's what it starts as. And then do you remember how you would change it so it has a denominator of 2? We times the top and the bottom by what? 2. All right, now don't forget, this is implied parentheses right there. So that 2 is going to get distributed in. All right, now you had a question. Do you remember what your question was, or do you want to let it go, or you had a question? Okay, good, you got it. All right, so I'm going to multiply by 2 in the top and the bottom. All right, now I'm going to just rewrite this to try to clean it up a little bit. You know what? I'm not even going to rewrite that right side, because one of the rules of proving, and this is something you have to know, is that you can only manipulate one side or the other in a true proof. Some teachers allow the kids to manipulate both sides, okay, and it is way easier, but I've been warned by many higher level teachers that no, if you're doing a proof, you can really only touch one side, otherwise you're making it easier for yourself. So you can't just do that to make it easier. You can only manipulate the one side, and I encourage you to, in this type of a problem, always manipulate the left side. We're going to keep doing stuff until it looks like the right side. All right, so let's multiply this puppy out. Oh, wait, maybe not. In one fell swoop, if somebody tells me the right thing to do, it's done. It'll be equal. The left side will exactly look like the right side. This is one of those moments where I'm very proud to have told you this at least 75 times in this class. If you can factor it, you should. Can you see it? Can you see something that can get factored there? Look close. Didn't I tell you that factoring would often solve the hardest problems that you had? Do you see something that can get factored out on the top? The k plus 1 is in both of them, isn't it? And once I pull it out, it'll be in the front, kind of like that, won't it? All right, so let's pull out the k plus 1. There's a k plus 1 in both of them. And they are both over 2, so my denominator is 2, so I can put them together and have a denominator of 2. And then if I factor out the k plus 1s, put them in the front, then they're gone. Technically, I'm dividing by k plus 1, but it's a lot easier to just say they're gone. And what do I have left? K plus 2. But wait, you say, Mr. Server, that's not exactly what the right side is. Oh, it's really, really close, though, isn't it? So if I'm going to just keep bringing this thing down, what do I have to do to make it exactly? Because you can't just say, well, it's really close, so good enough. Yes. Split the 2 into a 1 plus, wait, not 2 isn't 1 plus 2. Split the 2 into 1 plus 1. This 2 can be split into 1 plus 1. Do you see why I'm doing that? So that I can make that little thing. So I'm going to take another step here. Hopefully that doesn't, yeah, it went off the screen. There, now it's still on the screen. And I'm going to take this 2 right here, and I'm splitting them up. K plus 1 is still fine. K plus, and I'm replacing that 2 with a 1 plus 1. And it's all over 2. I get how this one and this one are identical. It's just I replaced the 2 with a 1 plus 1. And that's an okay swap, isn't it? Isn't 1 plus 1 the same as 2? So then, what does it need to be exactly identical to that? It needs parentheses. Can you just put in parentheses like this? Well, then you have to know, am I actually changing my result at all by putting in those parentheses? Can I group? Is it like 1 plus 2 plus 3? Is that the same as 1 plus 2 and then plus 3? Yeah, you can group things like that. There's a name for it. It is called associative. Very good. All right. And now I should copy down this that I've been dragging down over and over again and finally rewrite it. It's the same exact thing as it was before. And look, Mom, I proved it. Probably one of the hardest problems that you've ever seen, algebra-wise. All right, but certainly not impossible. Let's review what the steps were. Step 1 and 2 were child's play. Number 1, you stick in 1. But you have to understand what that list thing is doing on the left side. Okay, but other than that, it's super easy. You just stick in 1 and see if it works. We stuck in 1 and it worked. Okay, step 2. was you let n equal k. Again, super easy. You're just saying, I'm going to switch the variables. The reason you're doing it is you're saying, I'm going to prove this works even for any randomly chosen term. So instead of, I'm going to say, instead of n equals like 7, I'm going to say n equals anything. So n equals k. All you're doing is swapping n and k. So then the step 3. Step 3 is where all the action happened. That's where the A's and the B's will be separated. And that's the one where we had to put in k plus 1. Here's the step title. Step 3 is let n equal k plus 1. And you put k plus 1 on your list. Remember, that's a list on the left side. You just put k plus 1 at the end of the list. And then over here, you had to stick k plus 1 in. Then, this was the genius moment that only a few people see. That list is the exact same thing as the earlier formula because they say they're equal. It's set equal to it. So we can swap it out. And this gets replaced with this part right here. And then you had to do common denominators, and then you had to look at it for a long time, and many of you would have never seen it. But if you can go back to, that's why I use common phrases like that, so that when you're stuck on a test and you're like, I can't see anything I could possibly do, and then you go, well, maybe the factoring thing. Oh my gosh, it factors. All right. Okay. So that's one from start to finish. That's why there's only 3 on my paper, and one of them is your homework. Okay, so here's number 2. And the third one I'll give you, that's your job, is to try to prove that that one works. Okay? All right, so here's another proof. 5 plus 10 plus 15. You see what's happening there? Just think about this for a second. It's a little list where they're going up by 5 each time. Plus dot, dot, dot. Can anybody even tell me what I'm going to say next? It doesn't mean n, but it's not just an n. It's going up by how much each time? It's not n plus 5, no. It's 5n. I want you to think that through for a second. If I put in n equals 1, then I'll get 5. If I put in n equals 2, then I'll get 10. If I put in n equals 3, then I'll get 15. Okay, so there we go. That's the beginning of it. And is anybody actually smart enough to tell me what the answer is before I put it on the board? What do you think? Maybe if you multiply it all the way out, but mine looks different. All right, this is what it actually comes out to. It reminds me a little bit of that series thing where you take how many you had, and then you divide by 2, and then you do the first and the last. Anyway, well, here is the formula. We have to prove that that's actually true. Okay, who knows step 1? Remember it? N equals 1. So, step 1, I put in let n equal 1. So then, if I understand what's going on the left side, I don't just stick a 1 here and think it's all of these things. It's not. It's a list of how many terms in this case? 1 term. When I put in the 1, what is the whole left side then? When I put in the 1, I only get a 5. There's only 1 term, and it's 5. So 5 equals. Then you stick in your 1 over here. You get 5 halves times 1 plus 1. Does that actually equal 5? I'll just do a little bit more math. 5 equals 5 over 2. And 1 times anything makes it just go away, right? 1 times anything is just itself. 1 plus 1 is 2, so it's really times 2. 2's will cancel. 5 equals 5. Cool, it worked. Okay, n equals 1. Done. Now what's the next step? We've proven it for n equals 1. N equals k. I rewrite that whole honkin' formula. 5 plus 10 plus 15 plus dot, dot, dot plus 5k equals 5 over 2k, and then k plus 1. All I was is copying the formula, sticking in a k. That's why we don't make you prove anything at this point, is because it's got to be true if the other variable was true. I know this seems like an unnecessary step. I tried to get people who teach at the higher level classes where they really want you to know induction ahead of time before you get there. And they basically just said, that's just the way we do it. So please use K. So I'm switching it to K. Then we're going to take our next step, which is, anybody remember step 3? let n equal k plus 1. Yes, and so yes, you're going to add it to the list on the left side, because now this one I know some of you are going to mess up. Let's see who gets this one right. Try to stick the k plus 1s in the right places, and I'll tell you if you did it right in a second. I'm going to pause for a second while you give this a try. Okay, not having an abundance of time, I'm going to show you what you should have said. 5 plus 10 plus 15 plus ... plus 5k. Notice I did not take that off my list. I'm just adding another one. And do I just throw in k plus 1? No. How many of you caught that it's 5 times k plus 1? Raise your hand if you had that one right. Okay, good. I had technology intervene and wouldn't let me write a plus there for some reason. All right, now all of that, I'm going to move it over just so I have more room. Okay, plus 5 times k plus 1. All of that has to equal the other side, which I also put k plus 1s in there. 5 over 2, and instead of k, I put k plus 1, and instead of k plus 1, I put k plus 1 plus 1. So again, wherever there was a k, I have replaced it on that side with k plus 1. Okay. How many of you had that right? Okay, good. Now, I want you to just think this through. When it says 5 over 2, do you get that could have meant like over 2 like that? It would have been okay if it had been over 2 on the whole thing instead of having it in front. Now, I'm not going to change it to that. I'm just trying to make sure you understand that this thing is all one piece. It's all one big fraction that has a 2 on the bottom, really. That's a way to think of it. All right, so now let's do that swap that only one person could remember before, but I bet several of you can do now. How many of you already know what I'm going to do next? Get rid of what? The list. The whole list? No, only up to there, because up to there it was defined. Up to there is there. So that now goes here. So I'm going to put in a 5 over 2k times k plus 1 has to add 5k plus 1, because it's here, that's just me copying that down, equals, and I'm going to copy that down, 5 over 2. In fact, I'm not going to copy that down, because this is the part where that whole right side is going to stay the same for a long time. I'm not even going to touch the right side. It's kind of nice. You don't have to copy it down. You just put an arrow. Keep bringing the arrow down. If you want to put little ditto marks, that's the way some people do it. Kind of looks like an 11, though. Okay. Now, how are we going to get this whole thing put together? Who knows the first step? Yes. Yes, you could factor the k plus 1 out, but I would encourage you to actually wait just a second first before you do that factoring thing, because that's going to come up. But what did we do first before we did the factoring last time? Common denominator. Remember that? Okay, so let's get a common denominator. So over 1, so I can actually put this all together with a 2 under the whole thing. Then I'm going to times everything by 2, times this by 2. And now I'm going to rewrite it. 5 over 2k k plus 1 plus 10 k plus 1 all over 2. And since it's all over 2, and this one's really all over 2, then they have a common denominator, and it's 2. And what's on top? Don't multiply this out now. That was my biggest mistake when I was first learning how to do this, is I would try to multiply it all out. I should have followed my own rules, which is if you can factor it, you should. I should leave it factored. I know you could multiply this out, but then you're just going to have to refactor it back out again later. So it's better to not multiply that out. Plus 10 times k plus 1. And it's all over the common denominator of 2. I can put this 2 and this 2. They both had a denominator of 2. I put it all together. And now if I can factor it, I should. I factor out that k plus 1 out to the front. And then what do I have left once I've pulled out this and this? I have what? 5k plus 10. And it's all over 2. And you say, but that's not the same as the right side, Mr. Server. No, it's not. So it's your job to figure out what we need to do to make it look the same. Help me. Factor out the 5. I like it. We'll take this 5 right here that's in both of these parts. We'll take that out. And we'll have a 5 out in front, and a k plus 1, and then a k plus 10. No, 5 came out of that. So k plus 2, and it's all over 2. And isn't that getting really close to that? It is. All right, I'm going to grab this and bring it down. Yikes. Yes. It's really close, but it's not exactly the same. Same problem as last time. See that 2 there? What should I break it into? The 2 is really a 1 plus 1, right? So I'm going to replace this 2 with a 1 plus 1. And then I'm going to throw in an extra parenthesis here. And I should have done that in 2 separate steps to show you all the work. There it is. That's proven with induction. Okay, that's heavy-duty stuff. But basically, it boils down to 3 steps. Step 1, what's step 1 again? N equals 1. Step 2, N equals K. Step 3, N equals K plus 1. And then you got to stick the K plus 1 at the end of the list. You got to stick the K plus 1 in for K. Then you got to rearrange some stuff. And then you got to just mess with one side. Don't let anybody tell you should change the left side and the right side simultaneously. Yes, it is a lot easier, but it's also breaking what most people consider one of the fundamental laws of proofs, is that you can't change both sides of a proof until they equal each other. You can only change one side or the other. Most teachers are going to require that as you go into higher level stuff. Okay. It's hard, I know. I'm going to give you just one problem to do. Just one. This one. You ready? Prove that, I'm going to throw this out there. It's possible what I'm about to show you is not true. If so, you won't be able to rearrange it and make it equal. So either prove that it's true or prove that it's not true. Okay? By using induction. All right. 2 plus 4 plus 6 plus ... plus 2n. So far, does it seem reasonable to you? Okay. Equals n times n plus 1. Well, it's either true or it's not. Prove that it's either true or that it's not. If you put in the number, which you usually pick, which number do you usually stick in? 1. If you just stick in 1 and you know how to do it right, if it works, you should say to yourself, oh, this is probably going to work. And then you stick in n equals k. And then the third step's the killer. That's important to put in n equals k plus 1. You got to put it at the end of your list. And you got to stick it into the equation. Do some heavy-duty flip-flopping and solving, but only mess with one side. And that's all I have for you for teaching induction for today.